you. So 6 in the evening, thanks for coming to the last lecture. I know it's a long semester, so it's hard to arrive in person. Are there any questions before we move on and close Unit 8? Any thoughts, questions about Project 3? Yeah.
So will it assign the machine learning part? Is it correct that we're not caring what the numbers are? We're only caring about the orientation.
Right. So the question is about the part of the assignment where you're rotating digits. Yes, and in that case, you just treat them as generic pictures. It might get you thinking, saying, "Hey, if I would have just had, for example, a population or of digits 8, it might be easier to discover the orientation than combinations of digits, etc." And I think that for the final task there, you're also asked to merge both the fashion MNIST and the MNIST, right? So your model will learn how to recognize that things are disoriented or not at, it's 90 degrees, 270, 180, etc., or 0, based on those digits and the population of all digits. Okay. Oh, okay. So there was a question if it's taking a model that has a slope and checking if it's rotated. So that the one can go to such a problem and take all kind of constructive approaches where you're trying to, first of all, find what it is and then really do image processing like that. But that's not what we're suggesting. The machine learning approach is typically like a black box approach, where the machine is a child, and you show the child, this is straight, this is 90 degrees, this is 100, this is 180, this is a 0, etc. You show the child 60,000 examples, and then it kind of learns. Okay, so there's no, you don't need to do, and we're not asking you to take this approach. And the thing is that the machine learning approach often wins when there are large data sets. Okay, so you're not asked to do all kinds of calculations. The only calculations that you would need to do, and they're not too complicated, are in creating your data just to flip the image if you don't use a package, right? Flipping an image is a permutation of the pixels, right? But you'll need to figure out how to do that. That's not hard. Yeah. Other questions about the homework? Oh, we have people at home you can hear. Just please, if somebody can say on the chat that you can hear. If you can hear, yep, thank you. Thanks. Okay, so let me quickly review what we did. By the way, I'm viewing this now just for Mac users, so I'm viewing this on Safari. I just figured this one out, that at least on my computer, Chrome does not display some of the formulas correctly, where interestingly on Windows it does. So typically browsers should be operating system agnostic, but here somehow some of the formulas don't display nicely on Chrome, so I'm just going to look at this in Safari, just so you know. This is irrelevant for non-Mac users. Okay, so we talked about machine learning, maybe the engine behind AI, if you might call it, about supervised learning, regression, classification, about unsupervised learning, clustering, and data reduction. We've looked at ML data sets. Well, we looked at one. And in the practical tomorrow or the next day, you'll see the other companion data set, fashion MNIST. That's another. Of course, there are many others more complex. We saw that we can actually look at the data as a matrix like this. And again, for real big data sets, this is not something we'll really do, but I hope it was kind of instructive to understand what the structure of the data is. And then we looked at unsupervised learning and saw, well, used PCA. We used PCA from a package, principal component analysis. So we saw how to do some data reduction, very much from a user perspective. And if you do that particular part of the homework, then you'll need to do this in one of those tasks. And we also use the clustering algorithm. The homework doesn't ask you to do that, the project, sorry. And then we dove into detail bit by bit and went with the good old linear model, and saw how we can create a linear classifier. And linear models you understand from other courses, and even if you haven't really seen them in other courses, it's kind of sensible. You're just doing an affine combination of the features to get a prediction. And then your prediction is going to be, well, you're training it against a +1 or a -1, but the model is not going to give you exactly a +1 or a -1. And your decision was, well, is it positive or negative? And that's for a single digit. Yeah, what was your question or thought?
What is the word classify?
Oh, to classify, just yeah, I mean, how do I classify my children? This one is annoying and this one is nice. It's just sorry, kids, this is on YouTube, the problem. So not my children. They don't listen to me anyway, so they won't watch my YouTubes. But that's classification. Okay, so you put a label onto an object or something. So you classify an image. Okay, all right.
It's like a function of the data.
Yeah, that's a classification. Yeah, that's the term used. Okay, that's a term used in machine learning. Classification prompts, as opposed to regression, where everybody uses classification. Regression is a more mathematical term, but regression machine learning is to actually predict a continuous variable. Okay, all right. And then we put this in what's called a design matrix. This is also basic stats, and we saw in this case that, and then we decided on a loss function. Now, almost all machine learning problems have an inherent loss function. And the loss function is something that we often engineer for the problem, such that minimizing the loss is both computationally feasible and works, and minimizing the loss will ideally give us good performance, right? So we're not minimizing here the accuracy or minimizing the minimum of the negative of the accuracy. We're not maximizing accuracy. The reason is accuracy, differentiable, harder, etc. So we decided on this loss function in this case. Okay, and that's kind of the general gist in the ML world. In this case, we have the gradient of the loss function. What is the loss function from? What's the domain and what's the range of the loss function? This L, this loss function. What's its domain and what's its range? Right, R785, because we got 785 parameters in the range. It's a real number, right? We're talking about minimization. We're minimizing a real number, right? So it's a function from the parameter space to a real number. That's always your loss function. Now, in this very particular case of linear regression, then we can actually characterize this point where the gradient equals 0 and get this thing called the normal equations. And they actually have a solution using this linear algebraic term called a pseudo inverse, this A dagger. Okay, I think yesterday in the browser, this wasn't displaying as nice, right? Now, with the linear algebra package, and you can do this, by the way, also in MATLAB and also in NumPy, if you use Python, you can compute the pseudo inverse of the matrix, okay? And that means that to actually solve the optimization problem, we use this closed form routine pseudo inverse. And even if you don't have the closed form routine, you would compute the inverse of this matrix and multiply it by that. Although computing inverses is often something that you don't really do. You use other routines, okay? When this matrix is non-singular, and it often is, okay? And that gave us the betas, and we played around with this, and then we just put it in a classifier, and this is our classifier. We stuck in an image. Remember, we took one from the test set. We saw it looks like a 7. We stuck it in here, and indeed we got a 7. And when we do this in one go and try it on all of the test set, then we got an accuracy of 86%. Okay, and just a caveat again, accuracy is a sensible measure to use for classification when your data set is balanced. It's not a sensible measure to use when your data set is unbalanced. We're not dealing with that case in this course. Okay, and this is a confusion matrix. So now we're going on to the next bit, and I'll get this going. Just let's see if there's any questions further as I just set this up parallel. Sorry. Oh, I see. Let me just open a new notebook. Okay, so now with this example that's running, I'll speak about it as we. Oh, I see. when this example is running, I'll speak about it. What I want you to see now is a bit of just to get a feel for gradient-based learning. And in this sense, this is not looking good. What has happened here? Load error, undef string not defined. Into 25, line 25. Interesting. Oh, okay. So, sorry. This is the reason is this is part of kind of it was it was supposed to be a run in sequence with other using statements. Interesting that this thing in Julia, that's a very obscure thing, this letter L. I got an error about that. Has nothing to do with machine learning, just digression for a second. This is actually a macro. And in Julia, when you can do macros that are next to a string. And that's kind of just nice syntax. Okay, so this is a macro that comes from the LaTeX strings package. And that macro actually takes that string and converts it to LaTeX. Okay, and that was missing, and also the measures. All right. So what do I want us to look at here? So now let's look at a simpler problem. Let's look at just simple linear regression and start with this plot on the right and just assume that you have this cloud of points, X and Y. Okay, this is of course not the MNIST data set, not 784 dimensional, but rather your X's are only 1 dimensional. Okay, so your parameters are well, not 785 dimensional, but rather 2. So instead of 784 plus 1, it's 1 plus 1. Okay, and we want to fit a line that goes in there. Now, of course, you can do this with simple linear regression with least squares, but let's just see how this can be done with gradient descent. Now, with gradient descent, we would just take small steps and move in this parameter space in beta 0, beta 1 onto that point. But I've already shown you yesterday a plot of some gradient descent on some contours, right? In this case, this is stochastic gradient descent. SGD, stochastic gradient descent. This term is used a lot in the world of machine learning, of deep learning, etc. And let me explain what it means. Well, first of all, you don't even need my explanation because, gradient descent, stochastic, stochastic, a bit of randomness, okay? But in what way random? So you might think that it's just gradient descent where each time you choose the gradient, but then you kind of perturb it a bit. You don't go exactly down, you perturb it a bit. Well, that's not really what's happening. What is happening with stochastic gradient descent is that we don't use all of the data each time as we take a gradient descent step. We only use a subset of the data, and at one extreme, it's only one data point. Okay, so remember that the loss function, this discussion has a slightly kind of deeper meaning. This loss function that you already told me is a function of what? Is a function of the data or the parameters? You said what's the dimension? It's a function of the parameters. The data is kind of like a parameter of the loss function. It's fixed, right? The data is in there in the loss function. So each different data set has its own loss function, its own loss landscape. So when we do this and we compute the gradient, say like that explicitly, and we have a gradient vector, we know that for all of the data, this is going to put us straight down. An alternative would have been, we're too lazy for one reason or another to look at all of the data. So we're just going to take a subset of the data and we're going to look at the loss function associated with that subset of the data. Stochastic gradient descent chooses some random data point or some random subset. And hence our descent is a bit wiggly, but at the end it gets us pretty close to the optimal. Okay, so this fit here, this SGD, this blue line is close to the optimal fit, right? So that's what stochastic gradient descent does. Now, why? Why would we want to use stochastic gradient descent and not gradient descent? Okay, I kept on apologizing for MNIST. MNIST is just kind of running it on my laptop here, almost at the speed in which I'm speaking, right? Whereas as we speak, people around the world are training deep learning models, and as they're doing that, they're going onto Instagram while they're waiting to the computer to see updates and then go back because they wait a lot for the computer. Okay, so you typically just cannot compute the loss function with so much data. So stochastic gradient descent only takes a subset of the data. And at the extreme that we're taking here, it's just one observation. Now, this is sort of, it seems like a bit of a compromise. We're using stochastic gradient descent. And stochastic gradient descent, people kind of explored in the 50s. Everything almost in the field of machine learning, data science, applied math, etc., was kind of from the 50s. Because there was a horrible war, and then computers and a lot of knowledge, and then it kind of turned to good, or maybe we're using it again for bad, I'm not sure. But anyway, so the stochastic gradient descent was known in the 50s, but then people left it. And then when deep learning was revived, stochastic gradient descent became popular again. Why do you think it might be good to have a wiggly descent path and not kind of a very deterministic, nearly smooth path that puts you at the optimum? What would be a positive of having a wiggly path? Yeah. Oh, okay. So the statement was, if we're going to use, thanks, if we're going to use machine learning to approximate a stochastic pattern. I must say that this pattern here is not what we're trying to approximate. This is just a diagnostic of the model. Okay, in this specific, but it's a good guess, right? So in this specific case, the model has parameters that we can plot into parameters and we can see what's happening. As our buddies are sitting in another room, maybe PhD students here in the School of Computer Science and training deep learning model, right there, their thing is moving in a million dimensional space because their models have about 1 million dimensions. Okay, so it's not exactly that. But if you think of the loss landscape, in most cases, it's not going to have this very well-defined, unique, local minimum that's also a global minimum. There are going to be many local minima. Okay, and we can't plot it. I mean, it's 1 million dimensional. So with stochastic gradient descent, there's actually kind of this inherent also stepping out of local minima, so not getting stuck in local minima, so that it adds some stochasticity to the algorithm. But frankly, people are exploring this, right? So it's one of those things in machine learning that kind of works, and there's not this kind of worldly solution that, you know, or description why it works. Yeah. Right. So you're actually never going to find, yeah, you're going to find a slightly better minimum. Okay. Yeah. So you might be stuck in a local minima. Okay. So you're walking in the, so in Australia, we don't have this much. We don't have too many lakes, right? So and that are natural. So when you're walking on a landscape, you can always kind of follow it and get to the ocean or to the Murray-Darling and get to Adelaide or something, right? But if you go to, say, the Alps in Europe, right, there's a lot of lakes. You're walking, you're in this little lake, okay, but you actually, by being stochastic, you walk out and then you go elsewhere. Okay, that's kind of the idea. Now, you don't actually really want to minimize the loss function fully anyway, and there are reasons for that. We'll try to discuss that too. So this is not optimization. Has anybody done operations research here? No, we got some nice courses at UQ for operations research. So you might do. So there, you really want to optimize things because things that are deterministic, you want to optimize them. Here in machine learning, this loss function is, so this loss function is just a proxy for what we want to minimize. So it's not really our goal to minimize the loss function. We want to optimize accuracy or some other performance measure. Okay, so that seems to kind of work, and that's what has happened in this world. Just so you see this implementation, so this is kind of a complete bare bones implementation. It's not using a package or anything. Here we're iterating over the 10,000 steps of gradient descent. Okay, you never did when you did, even in high school perhaps, or in stat 1301, etc., simple linear regression, you never did the gradient descent, right? You did least squares formulas, which have an explicit solution with this sum x, y, etc., la 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 la. But here you're taking these steps. What are we doing in line 14? What's the rand? Just picking up on what I said. So random I would be what? An observation. So we're choosing which from all of these points we're going to go randomly by. And then here, this is an explicit expression for the gradient. So this expression that we see here in lines 15 and 16, this is a vector of length 2. This is exactly this guy, okay? Well, of length 2, not of general length. Okay, and what we're doing here, we're also just collecting the points and then plotting the path. All right, so I just wanted to speak about stochastic gradient descent, and just to finish it off, know that really what's done, this is kind of how our teaching works. We say this is done, and we say no, really you do this, but then no, really you do this. So really what is done is not stochastic gradient descent, but actually mini batch gradient descent. So if you'll speak to folks doing deep learning, then they speak about mini batches. What are mini batches? So you take your data, you have 60,000 data points, okay? You break them down into batches of say 100. And each time you just iterate 100, 100, 100, 100. So you don't choose randomly, you just do 60,000, 100, what's going to be 600 times. That's a mini batch, okay? So for each mini batch, you compute the gradient. So it's still a stochastic gradient because your data is shuffled, but it kind of repeats during the iterations. That's called mini batch gradient descent, and that's often what you see. And you'll see people speaking about the size of the mini batch, and you often choose the size of the mini batch basically based on how much GPU, graphical processing unit, memory you have, how much GPU memory you have. Okay, so that's a bit of deep learning folklore, maybe more than what we need. Let's move on to the next thing. And this is now directly related to the homework or to the project. Why do we call it homework? These are projects. All right. So again, I'm showing this on my Mac on a Chrome, and then these formulas show. All right. So moving on from the linear regression model, I now want to just have all kinds of warnings on this monitor, sorry. Moving on from the linear regression model, I now want to go on to what's called a logistic regression model. You've heard about logistic regression. You've done Stat 1301, some of you, you've used logistic regression. What is logistic? Some maybe not. Logistic regression is like regression where your outcome, from a statistical point of view, is regression where your outcome variable is not a continuum, negative infinity to infinity, but is rather constrained between 0 and 1. So it's a probability. Okay, so you typically, it's like the event of something happening. It's the most widely used model in the world of biostatistics. Medical doctors use it all the time, medical doctors doing research. Okay, how does it compare to the linear regression model? So take this guy here, okay? This B plus W transposed X, this is exactly, just written in a slightly different way, this is exactly this, beta 0 plus, you could say, beta transposed X, okay? So W is all your weights. But this is now using a bit of deep learning lingo, where B is your bias, that was beta 0 before, and W is your weight vector. Your two parameters that you're trying to find are the scalar B and the vector W. Okay, so if we put it in the language of what we'd had before, this is a scalar, one-dimensional, that was like beta 0, and this is 784-dimensional. This is an inner product, of course, right? Between W and X, and your one data point. So that's all nice and good. But then you don't just let this thing go out and fly and put you anywhere between negative infinity and infinity. You actually stick it in this function, which has become very popular, and it's called the sigmoid function. This sigmoid function, I'm going to do a horrible thing. Of course, you can plot it. Or, you know what? I'll just do this. I'll just Google it. Be super lazy and just Google it and not even plot it. I'll just write sigmoid function. And here it is. Okay, this is what the sigmoid function looks like. So you're sticking into the sigmoid function an output that was between. Sorry. Thanks. Okay. So you're sticking into the sigmoid function, into its input, something that runs between negative infinity and infinity, and you're getting a probability. So that's a sigmoid function, and analytically, it's like, it's this. Okay, 1 plus e to the minus u. Sometimes you see a different representation. You see a e to the power u times 1 e to the power u plus 1, right? If you multiply numerator and denominator by e to the power u. Okay, so that's a sigma. Now, this model has the same parameters as simple linear regression, but it cannot be optimized. There's not a closed form solution like this cheating trick. It's a beautiful cheating trick that we did here. We cannot do that. So whenever, even in stat 1301 or whatever, when you use R or anything, when you fit a logistic regression model, even for basic statistics, okay, it's doing some sort of optimization. Now, in the world of statistics, and statistics and ML, they're kind of siblings, but statistics is all about very nice models and not huge data and not so many parameters. ML is kind of more messy models, a lot of parameters, more data, slightly different applications. In the world of statistics, people optimize the loss function of, which I'm not showing you here, the loss function of logistic regression. They do it via second order methods. So kind of like Newton-Raphson variants. They use the Hessian. These are more complex methods than gradient descent. In the world of machine learning, when the number of parameters starts to be big, right here in our example, the number of parameters is 785. Again, you might have 1 million parameters. Gradient descent is still used. Okay. And what do? How do you optimize it? Well, kind of like the same thing we do here. You do steps, okay, and you take gradient descent steps. By the way, this was a main gradient descent step we had in the code below. We had our parameters, and we subtracted from them eta, the learning rate, times the gradient. Okay, you can take this example at home and change eta and see what happens. Change the learning. Okay, so that's logistic regression. Yeah.
So with this Y, like let's say we're doing it with the number series with the what would Y be in this case? Would it still be like negative?
Okay, no, great, perfect question, beautiful question, right? So what was your name? Joseph. Thanks, Joseph. So the question asked was, in linear regression, we had between negative and 1 and 1 but I kind of like that. I said we can do it between 0 and 1. The reason I like negative 1 and 1, it's not me, I didn't invent it, negative 1, 1, just because you say positive, negative, okay? Here, you're already getting a probability, and say we're going to do this in a second ourselves, right? So you're already getting a probability, and this is still binary classification, okay? It's still binary classification. And with this binary classification, let's say you're checking, is it a digit 3 or is it not a digit 3? Positive or negative, but your cutoff would be half. Okay, of course you can change that cutoff. Okay, so for a given, I'll stick in some image here, some sorry, you don't see it. Yeah, some image here. Some 784 dimensional vector. And then you will get a probability, and you'll see if that probability is greater than half, you'll say it's positive, otherwise it's negative. Okay, so that's logistic regression. Good news, practical eye tomorrow with our superb tutors, you're actually optimizing logistic regression. Okay, so you can do again one versus rest. You can train 10 different logistic regression models, and again choose the one that has the highest probability, right? And that's how you would say what is the digit. Okay, so it's still a binary classifier. So now let's move on to the big brother of logistic regression, or big sister. And that big sister is also called logistic regression. Depends who you ask. So statisticians will call it multinomial regression. Some people call it softmax regression, but some people just say logistic regression. So this is just like logistic regression, only that your output, this hat is still misprinting here. What we mean is there's a Y hat over the Y. So here, well, what do you think I meant by W being capital as opposed to a small letter? It's not a vector, but a matrix, all right? So here, what we're doing is we're not getting one probability. We're getting a vector of probabilities. This is a multi-class classifier from the go. So let's first of all see how this model works. You take your image, your 784 dimensional vector, X. Okay, that's your image. You multiply it by matrix W. Okay. In our case, this matrix is going to be of dimension 10 by 784. 10 by 784. All right. So you're going to get, it takes a 784 dimensional vector, you're going to get 10 numbers. Then you add to it this B. The dimension of B is also 10. you add to it the bias. This was just your affine combination. Okay. Now you're sticking it in the big, you're substituting it in here in the big sibling of the logistic of the sigmoid function, and that's the softmax function. All right. So what's a softmax function? Softmax function takes, in our case, let's say a 10-dimensional vector, but in general, a k-dimensional vector. All right. And that vector doesn't have to have things that are between 0 and 1. They can be anywhere between -infinity to infinity. There's no restriction on the range. It takes each element of the vector and it exponentiates it. Okay, so then these things are non-negative. Okay, exponent is non-negative. And then it divides by the sum of the elements. So what is a property of the output of softmax? It is a probability vector, a probability distribution. Okay, so if I'd stick in the numbers 3, 7, and 9, okay, I would get probabilities that are ordered such that 9 had, the thing that had 9 had highest probability, 7 had a lower probability, 3 had a lower probability. It's a mechanism of converting an arbitrary vector into a vector of probabilities. Machine learning has all this alchemy. Okay, this is like just kind of sticking things together, connecting things. Okay, just an alchemy of numbers. Okay, so the output here is then a probability vector. All right, so this is called softmax logistic regression. You're asked to do this in the homework, but we'll see in the project, but if in one of the tasks, but we'll see an example right now, and we'll do it. Now, this is already a powerful model. The linear regression example was, you know, kind of good for illustration purposes. This is already what you call a shallow neural network. Why is it shallow? Because it's not then doing it again and again and again and again in further layers and deep, and we're not doing deep neural networks in this course. Okay. So again, the parameters here are going to be this vector that's 10-dimensional and this matrix. Right? If you go into nuances in the world of statistics, then in statistics, there's really kind of the minimal parameterization. So you don't need all of the weights because you can kind of cut some corners and then things are not over parameterized. But in machine learning, you just have, again, this would be of dimension 10 by 784, and this would be of dimension 10. So we want to learn these two parameters. So let's do it. Let's first of all just copy the code again. And for this, we could have done it from first principles, but we're just going to use a package because that's complicated enough. I hope this will work here. Let's see. I just want to see that I have all the dependencies and everything's defined. Is this going to start to run? So this is what I ran before as we finished the lecture yesterday. Okay, warning that we can live with. No, this is not good. Okay, so let me just, sorry, I didn't. Okay, go here to lecture. Okay, I'll just set this up very quickly in this new lecture here. So I'm going to run this and something won't be defined. Sorry, I should have prepared for this ahead of time. But what we, okay, so end test, etc. So all that stuff. So lecture 2. I'm just going to copy a few things. Spec is just defining the data. So at this point, I don't think that we're using the data matrix X anymore. So we simply, for this to run, we loaded our train data, we loaded our test data. I'll show you in a second why we want the test data. And I hope that this will run now. and it's going to do gradient descent in this rather, oh, sorry, scrap what I said. We are using X. No, this is not what we need. I'm sorry, let's see. Where is X not defined? So if we go here, I don't see that we actually defined them. Oh yeah, X is this 2, 2, 2. Okay. One more chance, or otherwise I'll give up. But it's nice to see it running. And again, I apologize. Yeah. Oh, we don't need the heat map. That's too bad. It's gonna take a. And but I want to start to speak about what's happening here. Okay, as we wait for this guy, let's start to speak about what's happening. So we're doing gradient descent. All right. What's maybe the most important part of gradient descent? There may be two steps, two parts. There's one is compute the gradient, and second is do the descent step, right? So let's find these two things. This might be running now. We might be in business. I'm not sure. So computing the gradient is done in line 30. We'll work from the inside out. So computing the gradient is done. Yeah, this is working. Okay. So computing the gradient is done in line 30. And actually, we're using a function called gradient. What we're doing here is the main, I said this a bit yesterday, but I'll repeat again. The main functionality that a deep learning framework gives you, the kind of the most non-basic thing that it does, is gradient computations pretty much for arbitrary functions. And it's doing it using a form of differentiation, a form of gradient computation that Paul Bellet mentioned weeks ago. Not symbolic, not numeric, but do you remember there's like a third type? Not symbolic differentiation, not numeric differentiation, but automatic differentiation. He spoke about it very briefly. Automatic differentiation is the heart of deep learning frameworks. It's a mechanism, a computational mechanism for taking a function that's composed of subfunctions and using the multivariate chain rule in a smart way and computing gradients. The back propagation algorithm in deep learning is also an implementation of that. So sorry, I'm saying a whole bunch of things, but bottom line, I'm saying there's this kind of smart way here for computing the gradient. And maybe as your summer hobby, look a bit into automatic differentiation. It's powerful, right? This is what's happening here. Now, a caveat. I must say that for logistic regression, this is really not needed. This is not needed. Because just like or similarly to how that in linear regression, we have an explicit expression for the gradient, in logistic regression, you also have an explicit expression for the gradient. You can write it out, okay? Last year's project 3 actually asked the students to use that explicit expression in place of automatic differentiation. We're not worrying about it this year, so don't worry about it. But I'm still saying that logistic regression and softmax logistic regression within the world of deep learning models is still kind of special or gifted in the sense that you have an explicit gradient. It doesn't have an explicit solution to the minimization, but it has an explicit gradient. Still, we're doing it now here. Like any other deep learning model, we're actually not using any of that knowledge. Okay, and you might see this in your projects down the road, etc. You'll see, hey, I want to differentiate something. If you have an explicit expression, that's great because you can implement it typically in a better way than automatic differentiation. But here, this is just using it straight off the bat. The next important thing, please stop me at any point if there's something. The next important thing that you want to understand for gradient descent is how to do the gradient step. This is done here using kind of a black box using the update exclamation mark function given by Flux. What it's actually doing is using a variant of gradient descent called ADAM. ADAM is adaptive stochastic gradient descent, even though stochastic's not in there, that's what adaptive is. Adaptive stochastic gradient descent with momentum. That's what ADAM is, all right? The details are not so important. At the end of the day, it's kind of gradient descent, only that the steps are kind of varying. So this is, we can also treat as a black box. Still, as users of this is code that you do want to understand. As users, what are we doing? We're doing the main loop, which is the training loop. And how many iterations are we running this training loop for? I mean, is it a fixed number of iterations? What makes it stop? Where's the line that potentially stops us? Line 47, right? So we're saying, thank you. So we're saying if the loss value that we had in the previous step is not too far from the loss value that we currently have, then we stop. This is kind of a primitive stopping criteria. You could have maybe done it for a few steps because you're doing stochastic gradients, and this is by the way doing mini batch. So this internal loop is doing mini batches. Okay, so this kind of has the work. So this internal loop runs on subsets of the data, and each time doing mini batch. So each outer loop iteration is called, in the world of gradient descent machine learning or deep learning, it's called an epoch. An epoch? Sorry, so many terms you're getting here. All right. Well, I don't know if you're getting, but I'm throwing at you. So sorry for this variety of terms. Okay, but you don't need to become an expert. You just need to kind of get a feel for it, and you'll move with them on. I hope it'll be beneficial a bit down the road. So each iteration of the outer loop is an epoch. An epoch means that you've run over all your data. And within the epoch, you're running on mini batches. Okay, so that's just like the stochastic gradient descent. So as this thing ran, well, it's still running. I think it's maybe done. No, okay, I think it's finished in this case. Okay, we can probably run it again. So as it ran, we're getting a printout of each epoch. This printout comes here in this line where we're printing the epoch number. And we're showing the loss value. Now, loss value, it's nice to see that the loss is descending. Is it always going to be descending, or can we sometimes ascend a bit? It's stochastic. So we can have some bad luck, and the loss will, you can plot this. You can try and, just push the loss values into a vector and plot them, and you'll see it kind of goes like this, and maybe it jaggeds a bit. Okay, so we plot the loss value. But from time to time, we're also going to check actually the performance of the classifier. So what we do is we use line 43 here, and we actually use our classifier. This is just like the linear classifier, only it's a better classifier. Okay. It uses the trained parameters W and B that we keep updating dynamically as we go. And how often do we check the accuracy? Every 5 epochs. Yeah. So this is kind of common. We're not going to do one epoch and check the accuracy because this is just more time consuming. And it's very important this just took us exactly the time that I was speaking on my rather old laptop. Okay, or not so new laptop. But of course, again, you do this on a real problem, you can wait for hours. Right? So you don't want to check the accuracy every time. But look at the names of the data. This is X test, and this is the data here that we're using is from the training data. Is from, I guess you don't see this, but where is it? Training data. You use it from the training. We're iterating over, we're optimizing over the training data, but we're checking over the test data. So that's also important, right? So you don't want to check your accuracy over the same data that you're training on, because that can be misleading. And as I also said yesterday, sometimes you would keep the test data at the end, and you'd separate the train data, say use 40,000 observations for really training and 20,000 observations for validation. So that's why we called it here validation, even though it's over the test data. And you can see that the accuracy very quickly was at 70%. That's not as good as a linear classifier, but towards the end, we got to 92% accuracy. So we outdid the linear classifier. Yeah.
So with the batches, does that mean like every time we run a different batch, the loss function is going to be different?
Yeah, exactly. So every time, yeah, so this is kind of code, but there's kind of a lot of depth here. Okay, so what we're doing here is this loss function, and this is a bit that I omitted. The loss function for logistic regression or softmax logistic regression is called cross entropy loss. For your project, you could use a black box. You might have seen cross entropy in other probability courses, etc. Other things, etc. It's good. The name roots in information theory, but we don't have time to dig into all that. That's not as important. The fact is that it's a loss function that's suitable for like the probability distribution that you're all the time looking at. So you're all the time getting kind of the probability distribution, right? For every image that I put in, for every vector, now I get a probability distribution, a 10-dimensional vector, okay? And then I compare that probability distribution to the correct probability distribution. Now, what is a correct probability distribution? It's going to have 0, 0, 0, 0, 0, 1. If that specific thing is a 1, 0, 0, 0, 0, 0. That's how I compute it. Now, this loss is not on all of your data. It's only taking, this is a bit small, it's only taking the current batch. So this bit of code here is just a nice way of iterating over taking kind of 1 to 60,000 and iterating over batches. Specifically for this specific task, if you do that part of the homework, I recommend just unpacking this bit of code. Now, and of course, consultation hours will be open towards the end, well, until the week of submission, so next couple of weeks. Use Ed, etc. Deep learning frameworks, the fact that we're using the deep learning framework Flux, the magic that's happening under the hood, again, is really in this gradient step. And the W and B, these are your parameters. These are your weights, W, your weight matrix and your bias vector, okay? The same guys that we've seen here, W and B. Okay. The deep learning framework keeps those under the hood as kind of tracked parameters, as parameters that you keep optimizing on. So there's a bit of magic that's happening here. Okay, but yeah, this is a loss function with this, and look, the loss function takes that specific mini batch, and it takes the labels, the correct labels for that specific mini batch. You can try I suggest if you play with this, you can try taking this bit of code and just trying to change parameters a bit, for example, and then you kind of understand bit by bit. For example, mini batch size, what is our parameter for mini batch size? Where is it? I don't know. Say again? What line? 11? Oh, sorry. Sorry. Yeah, I used it as a keyword. Thanks. All right. So yeah, it's 1,000, right? So each epoch has here 60 iterations in an epoch. Okay. If I would have done mini batch size 1, it would have really been pure stochastic gradient descent. Okay. Now, this was all the good news, that this is what you need to do. The bad news is that there's one more lecture. You don't need to come. It's on video. It's last year's last lecture. I'll send it to Piazza, and that actually completes the material. So this year I took more time. I took it a bit slower. I felt that was kind of at the right pace. You actually have, say you're pressed for time and kind of had enough knowledge, because I mean, you can only do so much in a semester with 4 courses. Then you can skip that last lecture, but then that last lecture will deal with the decision trees if you choose to do the decision trees option. And it's kind of nice. So I'll just show you a second. So basically these beautiful things, which is a completely different machine learning algorithm. It's not gradient based, it's different. So I'll send the link to that last lecture from the 2022 course, and see you in the consultation hours. And thanks for the course. Thank you.